What do I mean? Let us look at example 1. Pure tension test. You know what I mean, right? Take a bar, pull it like that. So that's this. Let's see, where's the rubber band? Oh, there you go. So it's this. Grab two things, pull it. That's a tension test. So in that situation, is it obvious to you that sigma 11 is sigma? Everything else is 0. Sigma ij is 0 if I is not equal to 1 and j not equal to 1. Right? So that's pretty easy. So what happens then if you go to the full matrix? This entire thing is 0. So what will happen is you will get only the first row. Epsilon ij will be determined only by the first row. So the first row represents tension test in the one direction. So what does it have? What happens? So let us look at epsilon 11. Epsilon 11 is S1111 sigma 11. So notice in this case epsilon 11 will be S1111 sigma 11. That's all. All the others 0. Try it. Just multiply row by column. So if you do row by column, you will see that's what I'll get. So now we have a nice definition. So in a simple tension test, sigma 11 over epsilon 11 is called Young's modulus in the one direction. Hey, you may or may not have known that the Young's modulus, there is no one unique Young's modulus for a typical material. In each direction, you do a stress versus strain, and then you calculate the ratio. So S1111 is epsilon 11 over sigma 11, which is 1 over E11. In fact, S2222 equals 1 over E22 and S3333 equal to 1 over E33. So these are the three Young's moduli for the material. So if you go up here, this is a Young's modulus, 1 over the Young's modulus, that's 1 over the Young's modulus, that's 1 over the Young's modulus. Okay. But you can get even more than that. In a simple tension test, you can also get lateral strain. That means when you pull one of these things, and you know what will happen, right? Typically speaking, the y direction, the direction which I am pulling gets longer, but the x direction, that is sideways, this way gets shorter, thinner. We know that, right? So what we are going to do is, in a simple tension test, if sigma 11 is only not equal to 0, all others 0, epsilon 22 equals minus nu 21 epsilon 11. This is called Poisson's ratio. In the 1-2 plane, because there is nothing which says that in general, if you pull a material like this, how much it gets shrunk this way, there is no reason for it to believe it will get shrunk the same amount this way. You see what I mean? The two perpendicular directions may get shrunk by different amounts. So you got to have many different Poisson's ratio. So what we are going to do is, we are going to use this result, but according to our matrix gives epsilon 22 is S 2211 sigma 11, which turns out to be S2211 times E11 epsilon 11, right? Because sigma 11 over epsilon 11 is 1. So if you take that and put it here, you will get that. So this must be equal to minus nu 21. So S2211 equals minus nu 21 over E11. If you do the same thing, you will see that S3311 equal to minus nu what is it? 31 over E11. So we can start filling out this matrix in a slightly different way. So this term was 1 over E11. This term is minus nu 21 over E11. The next term is minus nu 31 over E11. These three things, terms here, will be discussed separately. Because they are trickier, right? Now, similarly, the next one will be 1 over E22, and then this will be minus nu 12 over E22, and then minus nu 13 over E33. Sorry, E22, 1 2 1 and then 3 2, and then minus 1 3 over E33, minus 2 3 over E22, minus 2 3 over E33, minus 1 over E33. So it will have 6 Poisson's ratios, 1, 2, 3, 4, 5, 6, and 3 moduli. 6 Poisson's ratios and 3 moduli. We'll look at this portion next. We'll worry about these two portions later. This portion is actually something quite interesting. Suppose you put sigma 2 3 not equal to 0, all others 0. This is a simple shear test. This is a very difficult test to do. So I'm just showing. This is actually called a pure shear test. But what I'm going to show you is doing sideways. This is not the way to do it, but I'm just showing you what the corresponding thing is. And there's a way to do it, but I'm not going to talk about it right now. But that's what you have to do to figure out. And then sigma 2 3 over epsilon 2 3 is called, so 2 times epsilon 2 3 is called G23, and this is called the shear modulus in the 2 3 plane. So these terms, where is that? There's my matrix. Let's see there. Yeah. So these terms are the 1 over the shear moduli. These things are the equivalent of Poisson's ratio for shear. So it's going to be, full of moduli and Poisson's ratios. Okay, so this whole thing is moduli and Poisson's ratios. This whole thing is moduli and Poisson's ratio. Diagonal terms, Young's modulus, 1 over Young's modulus, 1 over Young's modulus, 1 over Young's modulus, 1 over shear modulus, 1 over shear modulus, 1 over shear modulus, Poisson's ratio over Young's moduli, Poisson's Poisson's ratio over shear moduli, but this is a different Poisson's ratio. This is shear Poisson's ratio. That is, if you take a body and you shear it this way, apply shear stress this way, if it is not isotropic, the body will not just move in the same direction with the shear stress, it will move in some other direction. So, just like you get for Young's modulus. So, you will get cross terms. This thing is very interesting. This group and this group. This is called normal shear coupling. What it means is that if you take a body and you apply a normal stress, axial stress to it, it will actually not only extend, but it will also slide sideways. Not bizarre? See, imagine, so I'll show you, it's not as bizarre as you think. Imagine, there you go. Imagine you had a material which was full of fibers that were this way. Right? Now you pull it. What will happen? Not only will this gap distance between the fibers get extended, the fibers will tend to rotate like that. Can you see that? You will see that. I mean, if you pull something which has fibers in some angle, so what will happen is when you pull it, it will go like this. You can see it has become longer and thinner, but also it has sheared. So this shear strain due to normal stress, shear strain due to normal stress, is called shear normal coupling. Same way, if you take a body like that and you apply a shear stress to it, if you apply a shear stress to it, not only will it get sheared, not only will it become like this, it will also extend in this direction and this direction. So normal strain due to shear stress. So let me show you where these terms come. This is, so let's see, here you go. This is shear, let's see, normal strain due to shear stress. This is shear strain due to normal stress. This has 1 over moduli, and then these things are Poisson's ratio over moduli. These things have shear moduli, and these are shear Poisson's ratio. So you can see I get quite a bit of complicated stuff. To figure out what these are, we have to look at some specific cases, then you will see how this works.